Like, that was the whole problem, because we always have to push for, when, if you remember, like the soup over the history, this inside or outside, over the epsilons. So I think we already, where the soup is outside.
Right.
But then,
So, how is everyone?
All
Good?
right.
Yeah, all right. So last time we talked about harness of learning, something like really specific. So there's this input space which has 2 bits, that's just fast. And there's the target hypothesis, which says that if you take the first n bits and you compare, you take them, treat them as a number, as an integer, you compare them to the last n bits, and you find that the first n bits give you a number that's bigger than the second n bits, then the result is 1, otherwise the result is 0. Okay? And it turns out that this can be written in this form. You take the bits, you compare the bits 1 by 1, and multiply them with this 2 to the I. So just equivalently rewriting the inequality gives you this. Okay, so that means that this is a linear classification problem. In linear classification, you have, some inputs over some Euclidean space. You take the linear combination of the inputs and you compare it to some threshold, in this case 0. The result is compared to a threshold, in this case it's 0, and if it's bigger than or equal to the threshold, the result is 1 type, otherwise the result is the other type. Good? This is a linear classifier. And we're interested in whether a linear classifier like this can be efficiently learned exactly from samples. Okay? The samples are going to come from a distribution that kind of is a benign distribution. It covers the whole space. It's going to be the uniform distribution. So you take the uniform distribution over X, and you're going to sample some inputs from this uniform distribution. And after doing this, you record the responses of, I guess I put a star there because this is the target. You record the responses for all the n inputs. And the learner is going to see Z1, Zn, which is defined to be the sequence of pairs of x1 paired with y1 and x2 paired with y2 up to xn and yn. So this is the data that you give to the learner. This lives in this space of, I don't know, x cross y, where y is the label space, which is just 0 or 1 in this case because the indicator returns 0 or 1. And so this lives in this space. All right. So the learner takes the data and it's supposed to return the hypothesis. It's supposed to return a classifier. It's supposed to return a map that maps the input to the outputs. So a learner is going to be a map that takes Zn, an element of Zn, and returns a function that maps the domain x to y. Okay? Sometimes your learner is randomizing. It's a randomized learner. If you have a randomized learner, so that's one variation of this, then what you have is that it returns a distribution. Well, the learner itself usually is like you just sample from this distribution. You're not, the learner doesn't really give you the distribution. This distribution is both an enormous space, it's both function space. So in this case, you can think about that you have code for the learner, and if you call it code, it just returns a sample from that distribution. But nevertheless, you can think about the learner giving you the distribution, even though you only have sample-based access to that distribution. Yes?
I was wondering whether y to the power of x is the same as y to the power of n?
No, because x is 0, 1 to the 2 to the n. So the coordinate is much bigger, right? So n only appears here. There's a number of data points. And m is the size of the numbers. That's going to appear here. So if I write this out, it looks crazy. It's 0.1, 0.1 to the power of 0.1 to 2m. Okay?
I think the question is about the notation. Like, what does y to the power of x mean?
Yeah.
Oh, that notation. So that's like, usually people meet this thing in discrete math. So, yeah. Right. So that's, it's the space of all functions mapping from x to y.
Okay.
And if, like, we can talk offline about why that is the space of all those functions, but that's that. Essentially, this is like all f, such that f is mapping x to y.
Yeah, that makes sense.
Yeah. Okay. Everything's clear. So this is a learner. Every learner is such a map. Let it be, like learning a neural network, whatnot. If the neural network at the end needs to return a function that maps inputs to outputs, this is what's happening. And the learning algorithm itself, let it be gradient descent and whatnot, that's symbol A is representing that. Okay? So, in our specific case, the learner is going to see these examples. These are random examples. And the result that we are working towards is this proposition that says that take any learner is equivariant, and I will define what equivariant means to some transformation that I will denote by G. And I will define what this G is doing. So lots of things that are not defined at the moment. But I will claim that if you take gradient descent, initialized the usual way, randomly with weights and whatnot, then it's going to be equivariant with respect to that G that I will define. So it will satisfy these conditions. Or if you take a maximum margin learner. The maximum margin learner takes the data. So the data lives in this Euclidean space, but you can think about that this is a linear classification problem. So there is a hyperplane. On one side of the hyperplane, there are positive examples where the label is 1. Okay, maybe I should just write 1, 1. So there are these points. And then on the other side of the hyperplane, there are these other examples whose label is 0. And a maximum margin hyperplane would be the one that's kind of like sitting right in the middle, in the sense that its distance from the cluster of points, or the convex hull of the points that have identical labels, is maximized for both sets. That's the max margin. It's kind of like the most stable hyperplane that you can imagine. And that's going to be equivalent to, with respect to whatever G is going to be. So that would be a learner that people kind of like in these linear settings. It just sets the weights for the hyperplane. So in this case, the classifier is written in this form, right? And these weights are set in a certain way to have this condition satisfied. Okay. So let's take a learner like this that's accurate. Then if n is too small, so I want to say n needs to be large, or the learner cannot possibly return. Okay, so this is my data, dn, random. So let's put it this way. Then the probability that a on dn is not returning H star is at least 1/4, unless n is of the order of 2 to the n. Yes.
So if we have no restrictions on the learner, I could just return H star.
Yeah.
So this restriction is somehow not allowing me to do that?
Yeah. Yeah. The equivalent learner to my G, like the learner that just returns H star, is not going to be equivalent to my G. Once I define these things, it will be very clear.
Okay, I see.
Yeah.
And back to the things I was always saying about these hypothesis classes, is this way of restricting your learner, is there some way of mapping this to the learner has to return something from some hypothesis class or no?
Yeah, there's going to be some relationship to that, and we'll discuss that.
Okay.
Okay. But so the interest in this result is that we were discussing that we're interested in exactly learning something. So this is telling us that the learner will not be exact. It cannot return H star with high probability unless it has seen exponentially in the number of bits many examples, which is very damning because if you're thinking about, like, this is just a silly example or meant to be a simple example to illustrate the difficulty of exact learning when you apply it naively from statistical samples or like random samples, like passively learning. Our interest would be in learners that learn to reason, but they do that exactly as well. And so the connection to that is that Well, it's a little bit hand wavy. It says that, well, if you can't possibly learn this, like, why do you expect that, like, the input to that reasoning algorithm are going to be sequences of natural language text, which are long possibly, and the scaling with the length of the text, you can expect it to be way worse than this exponential scaling. This is a much simpler problem, and you already have these tremendous problems. Yes?
Yeah, so actually when I read the paper before this class, I had a question about why this proposition is interesting given a claim that happens before, which is you have something like, if I have a learner that needs to pick between two functions in a hypothesis class, and I want to do exact learning, and they differ on, like, those two functions differ on literally one input point,
Right.
then I can't even do it, because
Yeah.
if you
Unless you have seen an example that
yeah,
differentiates the two
but given that
functions.
you have no assumptions on the distribution, since you need to do well on everything, like you have to correctly label everything, even that is hard.
Yeah.
Why, like, I don't see why we're presenting this, like, more complicated story now.
Oh,
or-
I think that because this is what we care about. We care about teaching the transformer 8-star. Just this one thing. We don't care about designing a learning algorithm to make the transformer be able to pick up any algorithm whatsoever. We have no interest in that. What we have interest in is whether the transformer trained with neural networks is going to learn to reason. And that's just learning 8-star. So 8-star here stands for this particular algorithm of reasoning, right? And so all these other results that are talking about that, oh, you can't design an algorithm that able to quickly identify a hypothesis in a class of hypotheses, is like, yeah, the kind of, we'll see that underneath this proof, it's gonna be the same idea, but they're not directly that interesting because, like, it's a little bit indirect of like how you would use such a result. Like, using such a result is like requires some thinking, and this is what we are trying to get to. And this is what's actually interesting. And in most cases, this is like, you care about things like this. When you try to teach your learning algorithm to do something, you care about that something. You don't care about, well, if you are a designer of learning algorithms, maybe you care about designing a learning algorithm that is general, can deal with anything, and like, there's the designer's perspective, if you can do that. The user's perspective is that, well, I just care about whether you're able to design an algorithm that solves my problem. So these are the two different perspectives. And so here, we're directly answering this concern of the user, whether the designer was able to pick the algorithm to solve the user's problem. And we see that, well, no. If the designer is using algorithms of this type, it's not gonna happen. Okay?
So here, reasoning is kind of, we assume it's just this binary number.
Yeah, like we are oversimplifying reasoning to this decision problem.
Okay. And that's
We
okay.
say that like, oh, reasoning is more complicated. If you can't do this, you can't do reasoning.
Yeah.
Like, clearly you can't do reasoning. And like, reasoning would involve being able to solve this problem too.
And I guess you said this before, but it's, I think, only just making sense to me, is that, like in the normal learning theory stuff, we have the assumption on the hypothesis it can output, and here you're moving the assumptions to the actual design of the algorithm, A,
Yeah.
or like the learner A.
Yeah. Yeah. So these lower bound, but this is called a lower bound because it tells us that the number of samples needs to be at least that large. This is against specific learners. It's not against a learner that's completely arbitrary, because you could pick the learner that Vlad keeps talking about, his favorite and my favorite as well. If you have this problem that you want a learner that learns 8-star, you can have it. For any data that it eats, it should return 8-star. There, you have it. For this learner, You definitely cannot have this lower bound because this doesn't need data. This works for any n, right? And we had this discussion before that the reason we can't do this in the case of reasoning is because we can't write code to compute A star. In this case, you can. So that's a little bit of a mismatch, but like otherwise, general you can. And so this is a not an option there. If it was an option, we wouldn't bother with learning. This is called not learning. This is called like writing the code to do what you want to do. The trivial learner, yes.
Is this equivalent assumption is something like, for example, to mathematically saying that we cannot write the code instead of?
No,
Uh-huh.
no. That's nowhere in this. Like in this statement, there is nothing like that.
So maybe I can say what I have understood from statistical learning versus,
Yeah,
and please correct me if it.
yeah,
I mean, in the statistical learning, we have a hypothesis class,
yeah.
and the algorithm should kind of be approximately correct with respect to all of the hypotheses in that hypothesis class.
Yeah.
And the easier side than the exact learning is that the data and the tests are coming from the same distribution.
That's right.
But here we don't have the harder thing that we have than the statistical learning is that we don't have any assumption on the distribution. The distribution can be anything. We need to have exact learning over single data points.
I understand what you're saying, but I'm not sure everyone, yes?
Okay. But here we don't have any hypothesis class. We are just caring
Yeah.
about one single hypothesis H star.
Yeah. Yeah.
So that's the easier side with respect to the
Yeah.
statistical learning. Okay, good.
Right. But it's harder in the sense that you have to output the right solution, which is a function which should work for every input and not in a statistical sense. So what Elisa was talking about is that in statistical learning, you fix a distribution P. It could be the uniform distribution or whatnot. The training sample comes from that. Test sample is going to come from that too. And you're measuring performance with respect to such a random test sample, and you're asking what's the probability of a mistake. And if the probability of a mistake is low, you're happy. And the results say that that is not hard to achieve, provided that the hypothesis class that you are trying to learn has some nice structural properties. It has finite VC dimension. Okay. So that's the difference between statistical learning and this exact learning setting. So statistical learning, in a statistical sense, for hypothesis classes that are kind of small or structured, is easy. You have all kind of polynomial bounds, like you will not have this 2 to the m type of behavior there. Okay. So let's fill the gaps. So this appearance, so this G that we are going to have here is going to be actually three things. Gx, Gy, Gh. If I'm expanding it, Gx is an x to x bijection, and it's actually going to work on the bits by complementing the bits. Gy is a y to y map and takes a bit and returns its complement. So these are really simple. Gh. Gh is this thing that maps functions to functions. And if it takes a function h, then it's going to return 1 minus h1 minus x. Okay? For reasons you don't know yet. But it will become clear why I'm making these choices. In general, if you have a G that has these components, Gx, Gy, Gh, which are maps of this kind, could be other maps, then the missing definition is, what do you mean by A is equivalent to this G? And by that, what I mean is that if I apply G of age to what A returns on some data D, and that's the same, so it commutes with this operation. So, okay, let me write it out. So the algorithm takes x1, y1, x and yn, and then it returns a hypothesis. You take that hypothesis, you apply gh to it. So that's a hypothesis, that's a function, and this function should be the same as the function that you apply if you run the algorithm by first changing the data with gx and gy respectively, coordinated by, or like element by element. So gx applied to x1, gy applied to y1, and up to gx applied to xn, and gy applied to y of n. Right? This is the requirement of equivalence. This has to hold for all data, for all x1, y1, to xn, yn in z of n. Okay. If this holds, then we call the algorithm equivalent. If you have a randomized algorithm, there's a corresponding definition that I don't want to bother with. Maybe I should, but like, it's too much effort.
And this rules out that purple algorithm.
It does, right? Mm-hmm. Because if you try to verify it, like, it would just not work. Because on one side you will have H star, where A returns H star. On the other side, you will have 1 minus A star, 1 minus X, which we should write down, by the way. If you write down this G of H applied to H star, and then what it does at X, so this is the indicator, and then you have this sum, the coefficients, and then here you have to flip the arguments, because you have 1 minus xi plus 1, and you have 1 minus xi plus 1 plus n. The ones cancel each other, and the negative signs mean that the two arguments are flipped. So you will have xi plus n plus 1 minus xi plus 1 greater than or equal to 0. And so this just means that instead of saying that this returns 1 when the first number is greater than or equal than the second, it returns 1 when the second number is greater than or equal than the first. But then what this says is that you should negate that. Because when this returns 1, 1 minus returns 0, and when this returns 0, 1 minus 0 returns 1. So that's a negation to that. So now we are arriving to that this is the same as the indicator that the number, the second number, n plus 1 to 2 to the m, was greater than or equal, but you have to negate that, so that's smaller than the number that you had on the first m bits. So that's almost the same hypothesis as what we started with, except that instead of having equality of load, here you have equality of load, and you still return 1, there you have strict inequality. That's the difference. And now you can understand why things are gonna be kind of bad too. Because for the learner, because it has these equivalent properties, it will be hard to distinguish between these two guys. And unless it sees examples that it has that it shouldn't return this alternate hypothesis, it might lacerate to return that. And to see such an example, those are the examples where the two numbers are the same, are equal. Those are the only places where these two hypotheses are different. Those places, like, those are really special. There are only 2 to the m of them, out of the 2 to the 2 to the m possibilities. So you will have to wait quite a bit, right?
Here, did we make an assumption that the data distribution was uniform?
Yeah.
Okay.
Yeah. Somewhere.
Okay.
Yeah.
So you could
It's
give
a-
the data that's exactly that, and then it would.
That's right. So, if you wish, it also shows that if you can manipulate the data distribution, maybe you can manipulate the data distribution to your advantage if you understand what's happening with the learner.
But on the other hand, if you expand that set of G's, you could even remove that dependence probably.
You can, yeah, like, you can make the dependence, like, you can state a similar result for other distributions. It's gonna take more complicated form, less easy to interpret, so I just stick to it. So it's not that you cannot state similar results for other distributions. You can, but they might get weakened. Right?
What was the data distribution you said that would be very informative here? Or the data points?
So we can also think about what would be the most informative set. Well, you definitely, okay, so I guess maybe what you're asking is like what distinguishes between GH A star and A star. And those are the points where greater than equal is not the same as strictly greater. Those are the points where they are equal. The first m bits are the same as the second m bits.
Mm-hmm.
Those are, like, you have to hit that set to be able to tell these two hypotheses apart.
Mm-hmm.
Okay? All right. Consequently, if you know that you have a Mox-Machine learner, for a Mox-Machine learner that learns with these linear classes, you can show that you can always find linear in the dimensionality of the problem. So this is the dimensionality of the problem, 2m in this case. In that number, you can find linearly many points such that if you feed that to the learner, it will exactly identify the hypothesis. So these are the points which are on the margin, and uniquely identify the hypothesis. Not all sets on the margin, like those are the points which are kind of equal distance, like this is distance of 1, let's say. I just made up number 1. So there's a distance of the set. So in the case of this hypothesis, there are exponentially many points that are at equal distance, and they are nearest to the max margin classifier. And not all subsets of those are going to uniquely identify the hypothesis. So there is a lot of bigger room for that, for the hypothesis there. Yeah. But if you're clever, then you could select, if you try to teach the learner, and you know that it's a max margin learner, then you can select a very small cardinality, it's called a teaching set, such that the learner will exactly, after seeing those examples, will exactly output the hypothesis you want. Now, of course, we're not that much interested in these max margin learners. Okay, so why I'm talking about max margin learners, it's somehow connected to these neural networks. If you use cross entropy loss, you have this binary setting, and you use gradient descent, then in the limit of running gradient descent with this cross entropy thing, it converges to the max margin solution.
Basically over parameterized logistic regression.
Yeah. But this is only true for the last layer, and then people proved it for one hidden layer neural networks, and I don't think that the result is generally known, but like people kind of suspect that it could be true, but it's not quite clear whether it's going to be true. But it seems that the max margin thinking is not that bad. Like in terms of the neural network, like if it's an LLP last layer, if you think about that, it's just doing linear classification. Yeah, that kind of explains a little bit what's happening. So you're also learning the features. And of course, if I have a teaching set that's small, and I have a neural network that's learning features, that teaching set will not work. The neural network has way more degrees of freedom or symmetries or whatnot. And so it would need a much bigger teaching set. All right, okay, so let's get to this result. Like, how do we prove a result like this? Because that would be the point of.
A question.
Yeah.
So I'm not sure if I understood it. Like you're saying, if we have linearly independent features with a max margin learner, it can exactly identify it.
I didn't say linearly independent at any point. I said it like carefully selected points.
Okay.
Linearly many in the dimension.
Okay.
That's what I said. Linear, it's the cardinality. How big is this teaching set? That's the interesting question. And it doesn't have to be too big. Yeah. All right. So, this result is a corollary to a more general result that we want to prove, which goes like this. So, let G be a set of possible Gx, Gy, Gh transformations. Gx is x to x, Gy, y to y, Gh is mapping these functions to these functions. And so there is a connection here between GH, GX, and GY. And the connection is that if I apply GH to any hypothesis H and evaluate it at Gx, apply to X, is the same as Gy applied to H of X. So, all right, so here something about the notation. I didn't even notice that I'm doing this, because people do this all the time, which is that, well, when I wrote GHA, you should have shouted out, like, what do you mean? Well, I actually would need to put parentheses around everything. GH is a map. It has an argument. So this is what I should have written here, right? And here, Gx is a map. So it has an argument, xy. Same with Gy. All of these things. But then we would write so many of these parentheses, and it's kind of, from the context, you can work out where the parentheses are supposed to be, you just drop them. Okay? So I'm going to drop the parentheses. So here I have to add some parentheses because, well, it's not obvious that you apply GH to H first, and then that gives you a function, and then you await that function here. Okay. So there is this property, and it's, let's call it property, the compatibility property. So the Gx, Gy, and Gh maps satisfy this property. So this holds for every H in the function space. Satisfies. Right? We take this set. And we take an apparent learner. Oh. But it should be apparent with respect to every element of G. So this means for every G, in G, A is G equivariant. Like we use the earlier definition. Okay? Yes.
Wait, sorry. So GH is a GHH is a function that gets applied to GXX and then the
Yeah.
output. Okay.
Yeah.
Okay, that makes sense.
That's right. Okay, so A is G equivariant, and then let rho be a distribution over the domain, which is G symmetric. So the meaning of that is that for every G, in G, there's a Gx component. If I sample X from rho, it has the same distribution. And so I take G of X, it matches in distribution the distribution of X, which is matching in distribution rho. And this has to hold for every G. That is a little bit more general than the previous one. In the previous case, this capital G set is just a single atom. Go ahead.
Are we still constrain ourselves to the bit space?
The what space? Any X and any Y.
Okay.
Yeah. Maybe finite.
Oh.
So that it doesn't have to be, but yeah.
What does G equivariant mean again?
Huh?
What does G equivariant mean again?
G equivariant was defined here. Okay, so that was A is G equivariant if this holds. Yeah. So you can flip the order in which you're applying G. You're thinking about the elements here That's just like the single G that can be applied either to X or Y or a hypothesis. And when people write these things, a lot of times you drop the index X and the Y and the H, and it becomes just like a G applied to, no, I apply it to X, no, I apply it to Y, no, I apply it to H. And the meaning of that, okay, like that's different, but they're just maps. Yeah.
I'm confused by this G symmetry, this G, like the last line in the G symmetry, like the G X, random variable X equals to X.
In distribution. So equals and the capital D is on the top, that means equals in distribution. So they
Yeah.
have the same distribution.
But even that seems to like, for instance, like if, let's say X was just like a Bernoulli random variable with a parameter
Yeah.
that's not half, then if you apply G of X, you flip it.
Right? It will not be symmetric.
Oh, I see.
So here we're forced to use a symmetric distribution. And the only symmetric distribution for those maps, the
No, but wait.
complementary map.
How is that symmetric? Oh, that wouldn't be symmetric. You're right, I see. The case I gave
Yeah.
is not symmetric.
So here, the uniform distribution
I understand. Yeah.
is going to be G symmetric for all specific G.
I see.
Yeah.
But it's not the only symmetric distribution.
Not always symmetric.
Also, so I guess just in English, so is that equivalent the same as saying that if you give an algorithm a data set with all the x bits flipped, then it should return a hypothesis that will have
Yeah,
to be-
I should explain that it is kind of intuitive. This occurrence has an intuitive interpretation. It means that, like, if you're transforming your data in some way, then the algorithm should transform in a compatible way the hypothesis that it returns. So it shouldn't be sensitive to like the meaning of like what's in the data. Like it expresses this flexibility.
And in this case, the transformation is relabeling 0 and 1.
Yeah. Like relabeling 0 to 1, the algorithm is fed with the data, then if it's fed with the data, it should return the same thing as on the original data, but then you flip things in the output.
But there's still some interpretation of what 0 and 1 mean because of this equality check part, right? That's interesting. Like,
Well, that's just a
you know,
consequence of that 8 star is of this form. Like you would take some other 8 star, it would be different. Right. So assume that n is small. How small? 1 over the infimum for all G is such that GH is not H. Oh, fix an H. And you take the probability that H of X is not equal to GH of X. When I write this, G binds to H with high priority than the function evaluation. Okay, so first you apply G to H, and then you apply function evaluation. That means that here I could have written just GH, H, GX, X, and indeed this is what people usually write. And this GH, it's really G of H, H. But then it's too much clutter. So if I drop the X and the Y and the H, then this is what I mean. So assume this holds. So n is small compared to some inverse probability. then the probability that AD is correct is small. And here, D comes from the product distribution of Z. So if I sample the data uniformly at random from rho with the corresponding labels, and I sample and such examples, I feed this to the algorithms. That's my random D. I feed that. So this notation here, P of Z. So if I write P and a random variable there, that's its distribution. This cross N means n-fold product of this distribution with itself. So that means it creates a distribution over sequences of length n. And it's that distribution such that each component is, each marginal is this, and it's the product distribution. So that means if you sample from this, every component is going to be independent of the other components, right? So this is just a short way of writing that you had IID sample from PZ with n samples. Yeah.
Why not just write Z to the power of that?
Z to the power of n here.
No, it's the entire thing.
I don't know what.
The P,
Z.
The P bit. Up
Z?
until the comma.
Like without this?
And without the P.
This?
Yeah. And then make the Z bigger.
Okay. Okay.
Does that not make sense?
No.
Yeah, like people, this notation is not too meaningful.
I don't
Right.
understand the difference.
It's the distribution part.
Yeah, I mean, yeah, so usually this, like, if you write something to the power of something, that means that like you take some products. Whose products are taken and how do you interpret taking a product? There's no product like Z, it's just these pairs. Product is not defined for these pairs.
No, but we defined the distribution for Z, like the cursor Z, or is it a different thing?
Huh?
And that's D is like in the set of Z to the N maybe, but it's not this,
Yeah.
it's not sampled from that.
Yeah. So let's just keep this.
Okay.
By the way, so don't be too bogged down by this. This is just means that these Z1 to Zn, IID from rho. Okay? Actually, it will be important that we have these product distributions, but you can read upon them separately. I have not covered that. But we will use some properties of them. Yeah. All right, so we want to prove this. I have to actually done this. And we prove it by proving a lemma, and after proving the lemma, it will not be hard to see why this works. So the lemma is just stopping the proof before it's done. So D, Z, rho H, A, as before. No. Well, rho doesn't need to be, no need for G symmetry. So in this part of the proof, you don't use that. Okay, then you can prove that the probability that A and D returns the correct hypothesis is smaller than this quantity here.
No need, rho does not need to be G-symmetric.
Rho doesn't need to be G-symmetric for this result. For the previous result, once we prove this, we use that rho is G-symmetric. I don't want to repeat all the other conditions. That's the only difference in the conditions between these two results. Right? So what's here? This is the total variation distance between these two distributions. Yeah, by the way, here I should have said G is in G, of course. Otherwise, G plays no role, my capital G. So the total variation distance between P and Q is the maximum that you get if you compare the probabilities assigned by P and Q to the appropriate sets in the domain. And if everything is discrete, and I'm going to assume everything is discrete here for simplicity, then this soup is just max. Stuff like that. And it happens that this is the same as without the absolute value. You can convince yourself that that's true. We're gonna use this. This is statistical distance that measures how far two distributions are from each other. So is this, what's the proof?
What does GZ mean? GZ.
GZ. Yeah. G applied to Z, and you're right, I haven't defined that. If you take a Z, which is X and Y, and you want to apply G to that, then that would mean that you're applying Gx to the X component and Gy to the Y component. Okay? It's what you would expect. Okay. So there you took the random variable Z, and you take G applied to the random variable Z, you get the new random variable, you take its distribution, this transformed random variable's distribution. It's like you were flipping the bits, right? And then you compare the distance between these two distributions. All right. What's the proof? Well, we start to calculate this. And there is one key idea here. So fix a G such that GH is not equal to H. And take this set D, which is all the Z of n's, maybe I write lowercase d, such that A applied to D gives you H. Because if you do this, then you see that the probability that A on this random D returns H is the same as the probability under Z multiplied to itself n times awaited at S. So they're just like definitions. Like if you write out what the probability of the algorithm returning on a random D whose distribution is coming from here, it's going to return H, then that would be just the sum over all possible little d's that this happens. You take those exactly where this happens, and then you see that you're summing the underlying properties, you get this. Okay? So we're just using the definition. Right? And in this result, we're comparing GZ with Z. We already have Z there. So let's think about what GZ, let's think about what G of S is. And we're gonna see some nice things.
By the way, under the inf, did you mean GH not equals H?
Oh, yeah, not G, definitely.
Also, does there always have to be such a G that can, like, what if there's all the G's don't satisfy that? Like, I can pick an H. that says-
Yeah, I mean, let's assume that there is such a G.
I guess such an, yeah.
Because like, otherwise it's meaningless. Yeah.
I guess it's an assumption on your H.
It's an assumption, yeah. Exactly. And a G, capital G. All right. So, by the way, so this S, I use the letter S because these are the data sets on which the algorithm succeeds. So this is where you expect success. And so let's think about what happens if we apply G to S, by which I mean applying G to every D such that D is in S. So it's the usual definition of you apply a function to a set. And G is basically a function that you're going to apply to a set. And here the application of G to, these are tuples, n tuples. That's the same as what happened here. So this thing here, this is G applied to x1, y1, up to xn, yn, this tuple, which I now abbreviate with G, right? D, not G. Okay, so this is this set. So I claim that GS and S do not have any common elements. Oh, it's all right. So why is that? It's going to follow because GS is a subset of the complement of S. Why? Because if you take an element of GS, so let's prove this, that every element, like that GS is a subset of the complement. So what does this mean? Every element here is in complement, it's not in S. So take D from here. So that means that there exists D prime, D prime in S such that G D prime is equal to D. Just using the definition, right? It's coming from some element of S, which I denote by D prime. So what do we know about this D prime?
You want to use active.
What we know about D prime is that it's in S. So we know that if you apply A to D prime, then we are going to get what? H, right? And so now we want to verify whether D can be in S. To verify that, S was defined by the condition that AD is equal to H. We should evaluate AD. So let's see what happens with AD. So AD is, well, these are GD prime. So I can just use that. And A was equivariant, so that means that it commutes with G. I can move the G outside. Okay. And I know that AD prime is equal to H. So this is equal to JH. And I guess I took a G such that GH is not H. So this is never equal to H. All right. So that shows that indeed D can never be in S. D is in S complement. So we're done. Right? Now, now we are ready to start a proof. We want to bound this probability. We agreed that this probability is the same as applying this probability distribution to S. So total variation satisfies this. So a corollary of that is that I can take any set A and for any set A, the total variation is greater than or equal to PA minus QA, right? So if I want to upper bound the probability of any set A in terms of the probability of some other set, I can take the total variation and add the probability of this other set under the other distribution. So this means that this can be upper bounded as follows. Okay. So now is the same. This and the distribution of S under GZ is the same as the distribution of G of S under the distribution of Z. That's again some elementary manipulation of probabilities. So far so good.
And this doesn't need symmetric assumption?
No, I'm just moving the G from this argument to that. I didn't use symmetry. So now we're kind of almost done. I mean, you can upper bound. So this is a property of product distributions. If you have two product distributions, the total variation distance between them is less than or equal to n times the total variation between the two underlying distributions. Oh, sorry. this product n can be moved outside and you get something bigger. And you see that we almost got what we are after. So n times the total variation distance is there. And you might be inclined to upper bound this by 1, but that would mean that instead of this 1/2, you just have 1 here, and that upper bounds a probability, and that's trivial. So that's not good. So here comes the tricky part. You have this inequality, you add this probability to both sides. This probability is the same as this. Okay? So 2 times the probability that A is doing the correct thing is less than equal to n times total variation, distance between PZ and PGZ, plus the probability under this product distribution assigned to GS and S. And this is the point where we're going to use that S and GS are disjoint. If they are disjoint, the sum of their probabilities is upper bounded by the probability of the union of 2 sets, and the probability of any set is upper bounded by 1. So the sum of these probabilities is upper bounded by 1. So then you get this the inequality that we were after. Divide by 2 and you're done. Okay. So now it remains to prove the theorem. And if you see what's the difference between the theorem and the lemma, you see that all that we have to do is to upper bound the total variation distance to make it more plastic. And then reorder everything, and then this inequality is going to come up. All right. So we're going to show, actually it's the proof of the theorem. That is total variation distance between PZ and P G of Z, G is this before, is the probability that H on a random X is different than GH applied to the same X. An upper bound would be enough, but you can prove equality, so why not? And once you have that, you plug that in, and then you solve for the inequality. And then that's the result. So how does this work? We have to think a little bit about what this GZ is. So Z was X and HX. And you apply G to it. So that's the same as Gx applied to X and Gy applied to H of X. And because of compatibility, is compatibility gone? But believe me, this was the compatibility relationship. This is the same as GH applied to GX of X. the compatibility was set up such that this holds. We haven't used compatibility anywhere else. And now we can use that rho is G-symmetric. Because rho is G-symmetric, if you apply Gx to x, its distribution is the same as the distribution of x. So in distribution, this random variable is the same as x applied to x paired with GH applied to x. So basically, this is replaced with x, this is replaced with x, because they are identically distributed by assumption. All right. So let's call this z prime. So with this, we have proved that PGZ, the distribution of GZ, is the same as the distribution of z prime. So now we need to prove, we need to show that the total variation between PZ and PGZ is as we want it. Okay. Wow. Let's write out for clarity what this is. Z was just a pair XHX, and Z prime was XGH applied to X, this pair. All right. And now, if you do the sum calculation, and it's kind of quite trivial, then you find that this is actually this probability. Hint, you can choose A to be XY and XY such that Y is not equal to GH at X. And so you have this definition with the supremum, or that property, and assume for simplicity everything is discrete. You can write with sums, and you use indicators, and then you use the special structure of the distribution that the second component is deterministic. It's like either H applied to the input or GH applied to the input, and you can find that the maximizing set is going, one of the maximizing sets is of that form, and you read out the expression, and then you get this problem. It's just like a couple of lines of writing. Maybe it's a homework to get some practice with total variation. Happy to answer questions about it on Slack if you are getting lost. All right, so there's a proof. And that the theorem implies the proposition. Well, I guess it's kind of like obvious. You just have to calculate this probability for our special H, and that probability is going to be exponentially small. So this is 1 over 2 to the m or something, and then this becomes 2 to the n. All right?
Is it because the set of incompatible data point is very small to the number of holes?
Yeah.
Okay.
So it's kind of, I wanted to present this proof because, well, okay, so maybe you don't know about like how these lower bounds generally work. This works a little bit different. It's kind of similar. We didn't have a hypothesis space to play with, but you can play with the symmetries of the arc. We're basically saying that if the algorithm has this equivariance property, that means that it wouldn't be able to tell apart things until it sees a counterexample to that things that could be transformed are not transformed. Yeah.
Yes, so in this case, like we had the size of the domain was like 2 to the
2 to the n.
but the set of examples on which the two disagree, that is only 2 to the n, right? Not
It's the
2 to the
square root of the size of the domain, yeah.
Right.
It's kind of, I don't know whether that's a coincidence or you can push it further. But this is the best that you can get in terms of like the hardest example.
It's not
I
the
don't know.
square root, right?
It's the square root of the size of the
2
domain.
to the 2 to the n.
It's
Yeah.
2 to the 2m.
Like instead of 2 to the 2m, it's just 2 to the m. So if you take the square root of 2 to the 2m, like you slash the 2 in the exponent, yeah, this square root often comes up in similar things, so maybe it's not a coincidence, but I don't know.
Why is the infimum like exponential again?
So in our case, you take a random example x, uniform at random, and you want the first m bits to be the same as the last m bits. The probability of
I
that
see,
is 1
okay.
over 2 to the n.
I see, okay.
Because you have 2 to the m positive cases and then 2 to the 2 to the m for all the cases. So 2 to the m minus 2 to the 2 to the m to the m. You know what I mean.
So I guess if
So
you
that's-
fix the first m bits, then for the second m set of m
They
bits
have
will be the
to be
same.
the same.
Each bit has like 1/2 probability that is taken.
You can calculate this in many different ways. So, but that probability happens to be 1 over 2 to the m, and so 1 over 1 over 2 to the m, that's just 2 to the m in our case.
Isn't this equivariance thing weird to me still? Like, it's really bothering me that they're different on the places where they're equal for some reason. Like, cause like, it feels like the
I
assumption.
think you should, maybe what helps is to think about like what a neural network will do when its inputs are flipped.
Yeah, that's what I mean. Like, it feels like what you want to.
Or like, I shouldn't say a neural network, gradient descent, training a neural network which is symmetrically initializable to, like, it's quite an exercise to actually prove that these things are equivalent to these transformations, but they are.
We have some, for example, for the previous example, we had a specific G that, for example, flips X, flips Y, and also H.
Yeah.
And we saw that, okay, the algorithm is not working with respect to that G. Is this result kind of equivalent to we need exponentially many, eigen Gs, that if the algorithm is compatible with those, then it's the exact learner, or something like that?
There was nothing about exponential many G here. The more G you have, the larger that bound is going to be. So if an algorithm has more invariances, it's bad for it from the perspective of this lower bound, right? Because the infim gets smaller, your set G is bigger. By the way, maybe what helps is to think about another G, which would be reordering the inputs. Like the neural network has, I don't know, 2m inputs. And it treats all inputs the same way. Like it has no preference for like this input, like the first input is has a special meaning, I give it a bigger weight or something, it's not doing anything like that. So that's kind of the symmetry that the learner has. So if I flip in the data two inputs, it's going to output something such that if I flip the inputs for that thing, it would be the same as what I would get if I didn't flip originally the inputs.
So flipping during training is the same thing as flipping during inference, or like.
Wait, that doesn't seem right. 'Cause you're
It's
flipping
not,
the right thing.
not, okay, so if you didn't flip, you trained, you got something. No, you flipped, you trained, you got something else. What you got, if you flip for those inputs, is the same as what you got originally when you didn't flip. So that's the relationship, that's the equivalent relationship. And with this flipping the order of the, like, everyone feels that like that's right, like it's gonna work. It's a little bit harder to see that, like, if you're flipping just the 1 to the 0, then it kind of the same thing happens with neural networks, and you actually need symmetric initialization of the weights and like some technical properties for that to hold, but it's true.
But this proof also goes through with the other flipping.
It goes through with that, that other flipping is not suitable for transformers which have causal attention. But if you have transformer with causal attention, the token symmetry, so I call this the token symmetry, that you're changing the meaning of the tokens to some, like you are remapping the token space, either the input token or the output token space, remap. That symmetry is the transformer training with gradient descent still have. That's why I cannot use the other one. The other one gives the same result for MLPs and Marx margin learners, and it's much simpler. And with this other one, the GY transformation can be identical. It doesn't have to be. All right. Okay, so what's the summary here? Well, naively doing exact learning is not going to fly. And like people call these like algorithms pick up statistical shortcuts. Like people keep talking like image classification. It kind of looks at lower right corner, this pixel and such, and then there is a cow on the image, or like silly things. Algorithms do this. And when people talk about this, they never really define what the statistical shortcuts are, what they mean. Well, clearly what they mean is that the algorithm is not doing what it should be doing. It's doing something else. Many times, we think that the complication happens mainly because the neural network is very flexible, so it can do all of these things. This example actually shows that similar things can happen in very simple cases, linear classification already. So that's kind of, for me, really eye-opening, that I don't have to think that it's because of, like, the neural network flexibility can add to the problem, but the problem can already exist even for much simpler cases. And the problem is that the data is just not uniquely identifying from the perspective of the learner what you want to teach the learner. And to make it happen, that this unique identification happens, it's highly non-trivial. You have to work quite a bit for it to happen. And though we can go back to, okay, but in reasoning, we really want to have this property to happen. And so I want that to be always in the back of your minds. Like, how do we make this happen? Like, there are all these attempts already in the literature that are trying to address this. I don't think that any of the attempts in the literature are giving a satisfactory answer, otherwise we would have solved the problem. So it's like a big open problem. I think it's a big challenge of making these neural networks to talk to us in natural language and pick up the right algorithms. And one of the reasons this is a big challenge is because of this. Because this problem is highly non-trivial. Yes?
But isn't the answer what the exact learning people and their, like the exact learning framework exactly did, which is, isn't it like they basically noticed that, oh, if I am being faced with any distribution, which is technically the same as being faced with doing well on every possible input, right? Like any distribution shift is allowable.
Yeah.
Then like, the way I get my data cannot be coming from a distribution, but I need to be able to query what I need.
I mean, that's part, like, it can be part of the solution toolkit. That's active learning, right?
Yeah.
So empower the learner so that it can ask for labels for examples and so forth, actively learn. I don't think that that's enough. You probably want to also think about an algorithm to teach the learner. You know more about the problem than the learner. Basically, you want to transfer the knowledge to the learner in some way. And so you have a chance to, like, you don't have to design a general algorithm that for an arbitrary hypothesis class makes the learner figure out what examples to ask for. Like, we don't have that problem. The problem we have is that there is this single thing, reasoning, that we want to teach the transformer. And that should be a much easier problem than designing a learner that in the face of a general hypothesis class is able to figure out everything on its own. Like, that might be too hard. But we don't have that problem. We have an easier problem. So you can take advantage of that. You can design curriculum, you can write code that solves the problem, gives solutions. You can write code that evaluates the solutions of the algorithm, and so on and so forth.
Are there natural assumptions that people make over age? Because we know that language has some properties, right?
Well, or age star is this specific thing that we know it exists, we can recognize what it does. In special cases, we can write code for it. So that's not really an assumption, that's just like the fact that what H star is it's just given to us. You're not, like, we're still not solving a general problem. This is not about solving a general problem. It's solving a very specific problem, just one instance. And that's how it's different.
Mm-hmm.
And so, like, all these efforts that go into designing general algorithms, if it would work, it would be awesome, because general, of course, beats specific. They just don't quite work.
I guess I was not meaning the big H, but the small H.
Small h.
We know it has some properties, right? Like language has some properties.
It's not we know very little about the properties of language. We know the properties of, like, what good reasoning is. We know that.
Mhm.
So that part we know. That's not an assumption, that's just like the problem definition, right?
So what are the properties of that reasoning that people usually assume?
Well, it's following a set of predefined rules to arrive at conclusions, right? Like, so you could say that, okay, like, here's a math problem. Someone gives you that, like, this is my argument, this is the result. You look at it, and you can say, well, that step has a gap, that's not correct, or it checks out.
So we're talking about like logical
Yeah.
languages.
Yeah, but natural language is a superset of that, right? We don't want to require everyone to write a formal language, but that's one way to imagine that, okay, like, here was a math problem description in natural language, here's the equivalent formal language description, here is the proof in natural language, gives this result, maybe this translation of it to a formal language, Does the translation check out? Okay, someone needs to check that. Do we have rules for that? How the translation should? No. No one knows the rules. If we knew the rules, we could write the code maybe to do this transformation. We can't do that because natural language is just like too flexible. But it feels like it is well defined. Like we don't argue about that. Like this math problem cannot be translated to this. It should be translated to that. Like there's rarely disagreement. Like it could be, right? If you read the little book Mathematics Made Difficult, it's full of this examples that like someone makes a statement about like, oh, there are infinitely many numbers, like, oh, what do you mean by numbers? And like, and then you can talk about this like ad infinitum, right? But in everyday life, we don't really do this. We just agreed that like, we have ZF says is going to cover everything for us. And we stop arguing about it. That's a specific axiom system that mathematicians like to use.
So isn't this, so there's like this strange thing where we are saying, okay, this exact reasoning part is supposedly easy because we can write the code for it, but the natural language translation into exact reasoning, that is supposedly hard because we can't write the code for it.
Yeah.
And then this proof is saying that even the exact reasoning part is hard, like even forgetting about the natural language stuff.
No, if you want to learn it,
Uh,
it could be hard. It doesn't mean that code for H star or H is hard.
No, but yeah, if you want to learn it, that is hard. But so learning natural language on top of this is going to be even harder, right?
Yeah,
So
I
that,
think so. Yeah.
But
I think that this also kind of means that like naively expecting that you can just like the learner could try to do this translation to a formal representation and just learn the compiler itself. And if similar result holds for the reasoning setting, then that means that learning that compiler is also hard in this naive way.
yeah, but I guess it's just like the hardness is not coming from the thing that we expect to be hard, right? Like the hardness is coming from the part that we expect to be easy. Like talking about reasoning as being easy, but the natural language as being hard. And here there is no natural language in the picture, and still this is hard to learn.
Yeah.
So it's more like saying we want learning because we want to deal with natural language,
Yeah.
but learning is hard.
Yeah.
But it's not the same thing as saying that natural language is hard.
Yeah, so, yeah, the logical sequence is that because we want flexible systems, we want them to speak a natural language to us, not using a formal language, we can do that. And we can write the reasoning algorithms there, like there's no problem. This has been done many times. But if you want the flexibility, then you have to use learning. And then suddenly you open Pandora's box and like you have hardness results sitting around. Because you were forced to use learning because we don't know how to write the rules that deal with natural language. The only way we can do that, to deal with natural language to a satisfactory degree, is by using learning algorithms. But then we see that the learning algorithms are likely going to face, if we want them to also pick up reasoning as a side effect, even if it just means translating it to this formal language or whatnot, the math problems, why would that be easier than like learning to compare two numbers, right? Then you introduce this big problem that being correct on every example is going to be really tough because the learning algorithm can think about so many other ways of solving the problem. Like it has no reason to do the right thing. And during the history of learning, machine learning, we have seen this so many times, and it's been around, and it is around. It's not going to go away. So if you really want to use learning to deal with this problem, you really have to go hard and address this problem. Design new tools means maybe reuse the old ideas, but yeah, just means I guess I'm not a believer that you just throw more data at it. You don't do anything else, and it's gonna work. I think that examples like this show that that's doomed. It's not gonna work.
So where more data works is where you have like some fuzzy objective, like natural language translation. But as soon as you have a fuzzy language, but along with a very hard like correctness requirement, then everything.
Yeah, exactly. The hard requirement of correctness is not a big friend with the scaling of data. I mean, you can scale to the end. That's the answer. And like the domain is much bigger, right? Like this sequence domain is potentially infinite, right? Like the dimension is not even finite. Like what's the length of this? But one other interpretation of this result is that try to use learning for a small subset of the problem where this 2 to the m is not going to bother you. Then you can exhaustively sample. But then you have to reduce the bigger problem that didn't have the size restriction somehow to the smaller problem, and like we don't really know how to do that. But maybe that's how you should do it. Yeah. Okay. Way over time. But thanks.